Hello everyone, it's me Gagan Kumar present over here to teach you physics. Let's move on to the video. Today we'll be discussing electromagnetic induction chapter. So in this chapter, this is the topics we have to complete. So first is introduction, what is electromagnetic induction, and the experiments of Faraday and Henry, magnetic flux, Faraday's law of electromagnetic induction, and Lenz's law, motional electromotive force or EMF, motional EMF will study, and energy consideration, eddy currents, inductor and inductance, self-inductance, energy stored in inductor, mutual inductance and AC generator. So this is all the topics we have to complete here. So in electromagnetic induction, what exactly this thing is? Now the basic you remember. So when we started about electric current, so what we studied? We studied if a battery is there or a cell is there, then due to that electric current will flow in the circuit. Electric current will flow if a battery is there. So this is the main idea we have. But in this case, without this battery, we can have the current in the circuit. Okay. So this is the main idea about this one. So what they are telling, now electromagnetic induction is the phenomenon in which electric current is generated. Electric current is generated by varying magnetic fields is called electromagnetic induction. That means we will generate the current, electric current, by varying magnetic field. So we will not take this cell and all, external source and all will not take. Only what you have to consider? Now you have to consider some coils like this. Some coil is there. A galvanometer is there, one coil is there, and in this coil there is no external battery, external cell, external source is not connected, but still some current will produce if you bring a magnet near that coil. Okay, so this is the main idea about electromagnetic induction. So that is what they are telling here. They are telling us the phenomena in which electric current is generated or produced varying magnetic fields. Okay, so if you vary magnetic fields near a coil, then what will happen? Now here current will produce. So this is the main idea about electromagnetic induction. Okay, now basically one EMF also produce, electromotive force, potential will produce, that is called induced EMF, and this magnetic field is basically will check, that is magnetic flux. So by changing the magnetic flux will produce induced EMF. Okay, now so before discussing this experiment of Faraday and Henry, let me discuss about some magnetic flux. After that, we will come across the experiments of Faraday and Henry. Okay. Now, let's move on to the magnetic flux. So, what is magnetic flux? You remember previously we have already completed about electric flux. So electric flux basically will give phi E. Okay. So due to a charge, electric charge, so field lines will go like this. Suppose positive charge I am taking, field lines will go like this. Okay. And this is called electric field lines. So these electric field lines, how many electric field lines are passing per unit area or through a surface, through a given surface, how many electric field lines are passing? That is called basically electric flux. So that idea already we have. But here, similar way we'll discuss what? Now we'll discuss magnetic flux. We'll discuss magnetic flux. Magnetic flux. So here, magnetic flux definition is the number of magnetic field lines passing perpendicularly through a given surface is known as magnetic flux. Okay. So that means if a magnet is there here, if a magnet is there, north-south magnet, and you know from the north field lines will go towards south outside the magnet, and inside the magnet field lines will be from south to north, Okay. So here these are called basically magnetic field lines, or it is a uniform magnetic field line is shown here in this picture. So magnetic field lines are like this, and one surface is there. And this magnetic field lines, how many magnetic field lines are passing through the surface? Perpendicularly. Perpendicularly means normally, making angle 90 degree. So that number, or that is called basically what? Basically magnetic flux. Okay. So magnetic flux through a plane area A. Suppose consider a plane area A. This is the plane considered here. Placed in uniform magnetic field. So this is B is the magnetic field B. So field can be written as what? Now phi equal to B dot A. Magnetic flux equal to B dot A. So this A vector what I have given here. Now A vector is basically your area vector. A vector whatever given here. This A vector is area vector. Area vector. Remember. Okay, so there is a difference between area and area vector, or surface and area vector. So but this is the surface. This palm is my surface. Then surface vector or area vector will be perpendicular to the surface always. So how the surface will be? Okay, it does not matter. The area vector or surface vector will be always perpendicular to the surface. So this is the area vector you can tell. If this area, suppose magnitude I am telling A. So for this area, the surface vector or area vector will be perpendicular to the surface. Okay. So always remember that one. Now, so this is what area vector is given here. So flux equal to B dot A or BA cos theta, and theta is what? Now theta is angle between B and area vector, electric field and area vector. This theta is called angle between. Theta is what? Angle between magnetic field B and area vector A. Area vector A. So B is your magnetic field A. Already symbol we have taken. B. See, magnetic flux symbol is phi B and magnetic field is B, or magnetic field also sometimes called as magnetic flux density. So magnetic flux density also B. So this is the formula of magnetic flux. So B dot A equal to BA cos theta. Theta is angle between B and A. And always remember about area vector. Area vector is always perpendicular to the surface. Suppose this board is the surface, then where it is area vector, its area vector is this one, perpendicular like this one, pointing outward like this. This is the area vector. Okay. And remember, magnetic flux is a scalar quantity. So scalar quantity means it does not have any direction, or it does not obey any vector law of addition. So it is a scalar. And next, or you can check here, your dot product is there. So B dot A. So B dot A means definitely it is what? Your scalar product is there. Dot product, scalar product is there. So magnetic field is scalar quantity. So remember, the result of a dot product is always a scalar. Result of a dot product is a scalar. So it is a scalar quantity. And the SI unit of magnetic flux is Weber. So symbol is WB. Okay, so capital W and B you can write small b, and Weber you can write also, or Tesla into meter square. Okay, so because B is Tesla is the unit of magnetic field, SI unit of magnetic field, and area is basically what? Meter square. So Tesla into meter square will be the SI unit of magnetic flux. So apart from this SI unit, magnetic flux also will have CGS unit. So what is CGS unit of magnetic flux? Now CGS unit of magnetic flux will be Maxwell. CGS unit of magnetic flux is what basically? Maxwell. Okay, so remember this. And there is a relation between Maxwell and Weber. So 1 Weber equal to 10 to the power 8 Maxwell. So this is the whole idea about magnetic flux. So if a uniform magnetic field is there, then this is the formula you can write for magnetic flux. Suppose if a non-uniform magnetic field is there, what is the magnetic flux formula? That one we will discuss. So this small point you please note it down. So remember 1 Weber 10 to the power 8 Maxwell, And theta, what is this theta basically? Now theta is angle between B vector and A vector. And what is this A vector? A vector is area vector. Okay, if any surface I am taking here, suppose this is the surface here, this is the surface, then area vector will be perpendicular to the surface. Okay, so this is the surface and area vector will be always perpendicular to the surface. Okay, and magnetic flux is a scalar quantity. So here this magnetic flux, this value can be 0, can be positive also, can be negative also. So all can happen. So magnetic flux is a scalar quantity, so its value can be 0, positive, negative. Because it depends on cos theta. So in magnetic flux, that in flux, you have BA cos theta, 3 terms are there. Magnetic field is there, area is there, cos theta also there. So if the theta value is 0 to 90, it will be positive. And if the theta value is 90, then it will be 0. And theta value is greater than 90. So then what will happen? Less than 180, then it will be negative. So remember that. So depending on theta value, so flux will be positive, negative and 0. So this is the whole idea about magnetic flux. And suppose you want to change the magnetic flux, then if you change the magnetic field, then magnetic flux will change. If you change the area, magnetic flux will change. And if you change cos theta will change means what? You want to rotate the loop in a magnetic field. That time also magnetic flux will change. Okay, so this all things will discuss how magnetic flux can be changed. Okay. Now, next to come, if your magnetic field is non-uniform, so that means your surface is there and you can check here, this magnetic field is non-uniform. How to distinguish between uniform and a non-uniform magnetic field? Now here you see, these magnetic fields are equispaced parallel lines. So this is basically what? In one direction it is there. So this is basically uniform magnetic field. Okay, but here is check, magnetic field lines are like this. Magnetic field lines are like this. So if like this means your direction is not unique. And magnitude also not unique. So here more magnitude, here less magnitude, like that it is happening. So always remember, uniform magnetic field means it should be parallel, equispaced magnetic field lines. So these all are magnetic field lines. It should be parallel, equispaced. Okay. Now let's say next. Here, for uniform magnetic field, you can use B dot A. But for non-uniform magnetic field, what you can use? Now for non-uniform magnetic field, you want to find the magnetic flux through the surface. What you need to do? Now you need to do B1 dot dA1 vector. So you have to check each surface, and at that surface, small surface, at the surface what is the magnetic field? That small flux you should bring and you should add. You should add plus dot up to whatever thing is there, up to a number you can take. So this everything I can write as flux through the surface equal to summation over all the surface bi dot di. So this is the flux for a non-uniform magnetic field. Okay. Now sometimes what we'll use, now instead of the summation, what we'll do, now magnetic flux for continuous surfaces we can take as integration, that is basically surface integral B dot dA, or this area vector also can be written as B dot ds. So magnetic flux for a non-uniform magnetic field, you can use this formula, so integral formula. Okay. So summation over all written means over all the surface, small dA1, dA2, like that surfaces are coming here. So if that small surfaces I'll take and everything I'll add, I'll get basically total surface. That's why for a non-uniform magnetic field, your magnetic flux expression will be like this. Okay, so it is not B dot A normally, so it will be B dot dA, and here integration will be there. So this integration over surface. So this is called surface integral. Okay. So this is about your non-uniform magnetic field. Okay. So two things you understood. What is magnetic flux for a uniform electric field and for a non-uniform electric field. So keep in mind. And what is the SI unit of magnetic flux? CGS unit of magnetic flux, and what is the relation between them? Now we can move to some questions. So before that, just try to understand another thing. Suppose one coil is there, one surface is there. The surface can be any type. It can be circular, it can be planar, it can be like this also, planar, circular, like that. These are the coils. Okay. Or loops, like that one you can tell coils or loops. They can mention square loop, you can get circular loops. Okay. Suppose there are n number of turns are there. If n number of turns are there, if n is number of turns, okay. If due to one coil, your magnetic flux is phi, one coil magnetic flux is phi, then the total magnetic flux due to n number of coil, it will be n phi. So directly you can multiply. So total magnetic flux equal to what? N into phi. Okay. So due to one coil you find phi, or that phi if it is BA or BA cos theta whatever, then you like that. If many number of coils are there, then that number is basically n, number of turns is basically n, and total flux will be n pi. Simply you can add. Okay. And one more thing remember here. One more thing is, suppose you have a surface like this. If a surface like this, and in this surface your magnetic field is parallel to the surface. Okay, surface is there, magnetic field is parallel. For this surface, your area vector will be upward. This is the area vector, and area vector is making 90-degree angle with the magnetic field also, with the surface also. This is your surface. Okay, with the surface. Now in this case, if you want to find what is the flux, then what is the flux here? So flux symbol is basically you can give as phi b, that is your BA cos 90. So cos 90 is nothing but 0. So remember, when B vector is parallel to surface, or surface area, or parallel to loop, that time your magnetic flux is coming 0. Try to understand. What exactly happened here? One surface is there like this, and a magnetic field is parallel to the surface. Parallel means magnetic field is lying on the plane. Magnetic field is lying on the plane. So if magnetic field is lying on the plane, then here what is happening now? Already that surface area vector is perpendicular always to the surface. So that area vector always perpendicular. Here it is perpendicular area vector. Magnetic field lying on the surface. Now if you see this one, this is the magnetic field, this is the area vector, then angle is coming 90 degree. So between B and A, angle is 90. Okay. So remember, when B is parallel to surface or B is on the surface, that time your flux is 0. Why flux is 0? Now because in this case your B vector is perpendicular to A vector. So remember, when magnetic field is parallel to the surface, remember, magnetic field is parallel to the surface or magnetic field lies on the surface, that time your flux will be 0 because B and A angle will be 90 degree. So your theta will be 90 degree. So try to understand this. Okay. So many times they will ask how your surface and magnetic field is there. If a magnetic field lies on the surface or magnetic field is parallel to the surface, this is the parallel symbol I have given, parallel to the surface, then what will happen? Now B and A angle will be 90 degree and flux will become 0. Okay. Now next thing understand. So please note it down. And the next thing understand, if your magnetic field is like this and your area is like this, magnetic field is like this and the area is like this, that means your B vector is like this one and your surface is like this. So what is happening here? Now surface and magnetic field, they both are 90 degree. So B vector is perpendicular to surface. If B vector is perpendicular to surface, this is the perpendicular symbol, perpendicular to surface, that time area vector also in the direction of magnetic field. So area vector will be parallel to magnetic field. If area vector is parallel to magnetic field, then if flux I want to calculate, so what my flux will come? Now flux will come BA cos 0 degree. So that means it will come, flux will come BA. Flux will come BA. So magnetic flux. Remember why I am writing this magnetic flux as phi B, because to distinguish from electric flux. So electric flux is phi E. So this is to distinguish from that, I am writing as phi B, magnetic flux. So remember, when magnetic field is perpendicular to the surface, that time B vector, A vector becoming parallel, and magnetic flux is becoming B magnetic field into area, cos 0 is becoming, okay, cos 0 is 1. So this is the idea you must remember about magnetic flux. When it is becoming 0, when its value is not 0, you must understand this. Okay, so this everything will be written in language in question. So we'll see the questions there, we'll try to identify. If a magnetic field is perpendicular to surface, then B and A will be parallel. If a magnetic field is parallel to the surface, B and A will be perpendicular. So this thing you have to remember. Okay, so here the things are there, concept is here. Accordingly, you can apply this formula. This is the concept. From here you are understanding what is the theta value. So here theta value is how much? Theta value is 0 degree. Theta value is 0 degree. Then after your flux is coming out. Your magnetic flux is coming out. Okay. Now, next understand about questions. MCQ. How MCQ question will be there, you check. Now, so this is the first question here. The magnetic flux linked with a coil of n turns. So number of turns is given n turns. Area of cross section A. So area of cross section also given A. Held with its plane parallel to the field. So what is happening here? Now magnetic field is there through a surface. The surface is given like this. Surface is like this one, suppose. Now magnetic field is held parallel. So that means magnetic field on the surface. Okay. Then area vector will be how? Now this is your magnetic field. This is your magnetic field. Your area vector is like this. Area vector will be perpendicular to surface. Area vector will be perpendicular to surface. Okay. So if area vector is perpendicular to surface, that same area vector will be perpendicular to magnetic field, because magnetic field contains on the surface. The surface is like this, magnetic field also there. So here what is happening now? Between B and A, angle is coming 90 degree. Between B and A, angle is coming 90 degree. And magnetic flux, if you want to calculate magnetic flux, it will be BA cos 90. BA cos 90. So BA cos 90 is 0. So answer will be 0. So magnetic flux in this particular case is how much coming? It is 0. Okay. So magnetic flux is 0. So direct solution for this. Although a number turns is that, don't put this answer. This answer never be correct. Okay, because they told here with its plane parallel to the field. Plane parallel to the field. So see the picture. This is the plane and this is the field. So plane and field both are parallel. That means field lies on the plane. Field lies on the plane. Okay. So already you know area vector will make angle 90 degree with the plane. So if B also lies on the plane, area vector is making 90 degree with this magnetic field. That's why flux is becoming 0. Magnetic flux is becoming 0. So answer will be D. Now come to the next question. Okay. Now here a figure is given. Here one figure is given. Check here. So uniform magnetic field is there. Uniform magnetic field is there. So because straight line parallel, or they mentioned also here uniform magnetic field. Okay. Now area is given. Area is given. So area equal to 0.5 meter square. Area equal to 0.5 meter square. And a magnetic field also given here. So what is the magnetic field? Now magnetic field is given 2 Weber by meter square. Okay, you can write this also because Weber is Tesla into meter square. So magnetic field is Weber by meter square. That is also correct. Now making an angle 60 degree with the magnetic field. So this area is making 60 degree with the magnetic field. But they did not say anything here. But one picture is given. In this picture, seems like a perpendicular. So if this is your area, and this is your area vector. If that is your area, this will be your area vector. Okay. So area vector and magnetic field, they are making angle how much? 60 degree. They are making angle 60 degree. So magnetic field is like this. This is the magnetic field B, and area vector is like this. So we'll check angle between them. How much coming it is? 60 degrees given in the question. So that means theta equal to 60 degree. Now you try to calculate yourself now. Theta given 60, and for uniform magnetic field you know magnetic flux equal to BA cos theta or cos 60. So B value already given, it is 2, SI unit is there, so no need to change any unit. SI unit also given in area, so 0.5, and cos 60 value is 1 by 2. So how much answer is coming? 0.5. So magnetic flux is coming 0.5. Because 2 will get cancelled. So 0.5 Weber. So answer is 0.5 Weber. Okay. So don't get confused with this picture and all. So you don't take by mistake B and A angle is 30 degree. You don't take that because actually it is given. This dotted line like this is a area vector. That is a perpendicular to, if the surface is like this, area vector will be definitely like this one. So like this type of picture is given actually, and a magnetic field like that way. So angle is coming 60 degree between magnetic field and area vector. Now next question you see, magnetic flux is, some definitions are given here. Total charge per unit area, it is never. Total charge per unit area is nothing, not magnetic flux. It is actually surface charge density. Total current through a surface, this is also not correct. Total number of magnetic field lines passing normally through a given area. So this one already we discussed. So magnetic flux is basically the number of magnetic field lines passing perpendicularly, or this perpendicular reward also can be written as normally. Okay, so this is the answer. So D cannot be answered as it is MCQ question. Total EMF in a closed circuit, it is not correct. Okay. So now come here. Next question. So here answer is C correct. MCQ, here it is a accession and region type question. Magnetic flux is a vector quantity. So this is definitely false. Okay. So already we discussed here that magnetic flux is a scalar quantity. So accession is false. Now region, value of magnetic flux cannot be 0. So value of magnetic flux can be 0, can be positive, can be negative, but they are asking here it is can't be 0. So this is also false. So accession also false, region also false. So now very easy to identify, you check here. So here it is written D if both accession and region are false. Okay. So remember magnetic flux is a scalar quantity and its value can be 0, positive, negative. So based on that they asked here. So your D answer is correct. Okay. Now if area vector A vector is given 3 I cap, 2 j cap, 5 k cap, and magnetic flux density, that is 5 I cap, 10 j cap, 6 k cap, the magnitude of flux linked with the coil. Okay. Now here area vector, magnetic field, both are given in vector wise. Now the magnetic flux linked with the coil is what? Now to do this, so what you have to do? Now here magnetic flux we know it is B dot A, and normally you do for what? Normally we calculate B A cos theta, and theta value substitute, B will be given, A will be given, we will put directly, but it is not given like that. So if it is not given like that, so what you do? Now suppose if here B vector is given like this, B1I plus B2J plus B3K, and A vector is given A1I plus A2J plus A3K. If vector wise given like this, component format is given like this, then suppose you want to find magnetic flux. So dot product rule it is. Now what you do? You do like this. You do B1 A1 I cap component you multiply, J cap component you multiply, K cap component you multiply, I cap component, J cap, K cap you multiply. Now do the same thing here. Now here A vector is given, B vector is given, all component wise given. I just multiply and try to calculate the magnetic flux. Now here it is 5 into 3 plus 10 into 2 plus 6 into 5, so 15 plus 20 plus 30. Now this is 35 plus 30, so which is coming as 65. So magnetic flux is coming 65 Weber. 65 Weber. Let's check everyone. You calculate yourself and check. Answer is coming 65. Simple thing. If you remember dot product rule, so scalar product or dot product rule, if you B vector, A vector given component was like this, and if you are calculating their dot product, then simply multiply I cap coefficient multiplication plus J cap coefficient multiplication plus K cap coefficient multiplication you have to do. Okay. So answer is coming 65. I hope you understand. So magnetic flux we completed with the questions. Now let's come back to our main experiment, Faraday's experiment. So Faraday's and Henry experiment will discuss. So magnetic flux part we completed here. Now the experiments of Faraday and Henry, actually what they produced electric current by changing different setup, experimental setup. So that setup we'll see. So there are particularly 3 types of arrangement is there. So that one we'll see here. After that we'll go to Faraday's law. So see here, what are the experiments of Faraday and Henry? Now in experiment 1, so they have taken one coil. Here they have considered one coil, and here one bar magnet and one coil. Now in this coil there is no external source is applied, just one coil with a galvanometer. So galvanometer just to detect the current in the circuit. Now this magnet is brought towards the coil. So when a magnet brought towards the coil, so what happens? Now the magnetic field lines are coming, or basically magnetic flux are coming. That means magnetic flux will be there through this coil, because you discussed already magnetic flux, the number of magnetic field lines passing per unit area or through a given surface, that is called basically magnetic flux. Now here see, so here what is happening? Now here when magnet is coming, many flux, many lines are coming towards that coil. Okay, so your flux is increasing. So previously when magnet at a far distance, so these field lines cannot reach this coil. Okay, suppose this magnet is at a very far distance here somewhere. So these field lines cannot reach here. But when magnet comes near, these field lines are reaching that coil. That means some lines are passing through the surface. If lines are passing through the surface, then definitely some flux will be there. So previously zero flux, when magnet came, some flux is there. So there is change in flux is coming. So due to that change in flux, some current is developed. So that is what basically here Faraday's law. So current is inducing, that is induced current. So this is the arrangement they saw. So in experiment 1, this is the experimental setup. A bar magnet is there, a coil is there. If a bar magnet brought near the coil, or you take also coil near the bar magnet. Okay, then what will happen? Induced current will produce. So this is the setup you do, coil you do, magnet you do, and you can write here. So this is your figure. So what this figure basically what telling? Now figure is saying, or experimental setup is saying that when bar magnet is pushed towards the coil, the pointer in the galvanometer deflects. So experimental setup you do. In this experimental setup, what we observed? So some observation will be there, and after observation, one conclusion will be there. What is the conclusion here? So remember, whenever this magnet is stationary, so magnet is not moving, that time there is no deflection in galvanometer. Only when magnet moves, either comes in or goes out, then what happens? Now here induced current will be there. So that means definitely the relative motion is the cause of electromagnetic induction. So relative motion between coil and magnet. Okay, so that is what we will write in observation and conclusion. So when the north pole of a bar magnet is pushed towards the coil, the pointer in the galvanometer shows deflection, indicating presence of electric current in the coil. And the deflection lasts as long as the bar magnet is in motion. I told you that if a bar magnet is stationary in a place, then no flux change. So no induced current. Now the galvanometer does not show any deflection when the magnet is held stationary. Okay. So what is the conclusion you are saying here? Now the relative motion, that is what I told, either take magnet towards coil or take coil towards magnet, the same thing will happen. So that's why the word we are using here, relative motion between the magnet and the coil, that is responsible for the generation or induction of electric current in the coil. Okay. So two observation and one conclusion you write for this particular experiment. So remember in Faraday and Henry experiment, in experiment 1, so they checked about a coil and a bar magnet. And this is the experimental setup, and this is your observation and conclusion. Observation and conclusion. Okay. So you can write this experimental setup after completing this picture and all. Then you can write what about observation and conclusion. Okay. So now I'll go to the next experiment 2. So what experiment 2 is saying? Similar way, instead of a bar magnet, you take a coil. Instead of a bar magnet, take a coil here. The previous coil 1, this coil C1 was as it is. One galvanometer is connected, C1 is there. Now take a C2 coil. Now this coil, here one battery is applied or potential is applied here. Potential is applied. Due to that one, some current is going, some battery is there. So due to that current is going. So due to that current, your coil is there, coil I am telling, there are many turns are there also. So you can assume like a solenoid actually. So what is happening here? Now in this coil, there are some magnetic fields are producing. Magnetic fields are producing. And here, this is acting like a north pole and this is acting like a south pole. That means it is equivalent type a bar magnet, like that it is acting. Okay. Actually, we are not taking bar magnets. We are taking a coil, but it is equivalent to a bar magnet. Okay. So same thing we did when we two coils, one coil is stationary, galvanometer only connected, no any other external source. Only another coil, one battery is connected, and we brought towards the coil 1, towards this coil. This you consider as C1, C2, consider like that. Then what is happening here? Now here also, current is producing in the coil 1. So in this coil, left side coil, current is producing. Why it is happening? The same phenomena, whatever you understood there, the same way it is happening there. So magnetic flux is changing here. When it is coming, more magnetic flux. When it is going away, less magnetic flux. When it did not come, that time no magnetic flux actually. Okay. So like that it is happening. So that's why here what happened? Now here magnetic flux changes happening, induced current is producing in the coil 1. Okay. So in the experiment 2, similarly we will write 2 observation and 1 conclusion. So what is the conclusion will be here? Now instead of bar magnet, if you are bringing a current carrying coil towards another fixed coil, connected with a galvanometer, then what will happen in this coil which is connected to galvanometer, their current will produce or induce. Okay. So that is what we will write here. You see this. So you can do this setup. Then you can write the observation for this. So what is the observation here? Now as coil 2, that C2 is moved towards the coil 1, the galvanometer shows a deflection and this indicates that electric current is induced in coil C1. And when C2 is moved away, the galvanometer shows a deflection again, but this time in the opposite direction. Okay. So galvanometer, galvanometer deflections will be like this. So this will be 0 and here this will be the pointer like this one. So like this it can show the deflection galvanometer. So here in opposite direction, when you are taking away in opposite direction, deflection is happening. And when deflection lasts as long as coil C2 is in motion. Okay. Till this coil C2 is in motion, that time what is happening? Current is producing here. If it is at rest, no EMF, no current, no deflection here in this coil 1. Okay. So that means if there is a relative motion between 2 coils, okay, one is connected to voltage or current carrying coil, another is not carrying any coil. Okay. So then what is happening? Now EMF is inducing. That is what the conclusion you write. Now the relative motion between the coils that induces the electric current. Okay. So that means in the 2 experiment, that experiment 1 and experiment 2, the word basically you are using what? Relative motion. So either relative motion between a coil and a magnet or relative motion between 2 coils. Okay. So relative motion word we are using here. Okay. So you can write this 2 observation and 1 conclusion here for experiment 2. So these all are basically Faraday and Henry experiments. Now next we will go to experiment 3, which will say this relative motion is not required. Okay, something other setup will do. Basically Faraday did this. So here what we did, now 2 coils we kept. Okay, just consider this is C1 coil, and you can consider it C3 coil or C2 coil, anything you can consider. Let me call say 3. Okay, because C2 we took for that current carrying coil. Okay, so here we are taking as C2, let's C3 take, no worries. Now here what is happening? Now here in this coil, external potential is there, battery is there, but one switch is there. This is called tapping key. Okay. So what is this tapping key means? Now here, if you want to close the circuit, you want to current in the coil C3, then what you do, just close that key. Okay, switch on that. And you remove that connection, then current will be not there. So that is what basically. And both are stationary. So this is at rest, not moving. This coil also at rest. Rest means not moving. But what the arrangement is there? Now both the center, some common axis is there. Like this arrangement is there. So coaxial arrangement. Okay. So remember here no battery connected, only galvanometer, just to see the deflection current is there or not. Okay. So here it is basically tapping key is there. Now what observation we did? Now galvanometer shows momentary deflection when the tapping K tapping key K is pressed. That means when you are closing the circuit, that time current is going. Due to that current, some magnetic flux changes happening here, and due to that you can see some deflection in galvanometer. So if you will press this like this, key is like this one, key is like this is the K, okay, tapping key. If you will press this, here you can see the deflection in galvanometer. Now again you remove that, again you will see the deflection, and if you keep pressing, you will not see any deflection. So why at the time of pressing and at the time of releasing this key, that time only we see the deflection. Okay, so because that time only current, when pressing the key current is there, when not pressing or you are releasing that time what, current is zero. So current is increasing, current is becoming zero. So due to that flux changes happening, that's why here current is, what is happening now, current is producing induced current. Okay, so this is what the experiment here. So what in this experiment, remember both the coil are at rest and they are coaxial, and here one coil is connected with what, battery and a tapping key, and another coil is connected with a galvanometer. Okay, so what will be the observation here and conclusion? The conclusion I told already. So they are both are at rest. After that also some induction of current is there, induced current is there. So definitely no relative motion is required. Okay, that is the conclusion. And observation, whatever you observed now, you can write that. Okay, so you can write this experimental setup. So complete this experimental setup and write these observations. So this all are 5 observations are given. The pointer in the galvanometer returns to 0 immediately, and if the key is held continuously, pressed continuously, then there is no deflection in the galvanometer because there is a steady current is there. Okay, but when key is released, that time only deflection is there because current is becoming 0, from maximum to become 0, because releasing means circuit is open circuit. Now the deflection increases dramatically when an iron rod is inserted. Also, if you insert one iron rod also, that time also there is some deflection increases. So that also point to remember. Sometimes theoretical questions can happen. And understand about conclusion. So what is the conclusion here? Now Faraday showed that the relative motion is not an absolute requirement. Okay, that is what I told. So relative motion is not needed. Okay, so we can, by tapping key also we can produce induced current. Okay, so that is what the conclusion you have to write here. So this is all about theoretical knowledge, Faraday's and Henry's experiment. Okay, so for this all 3 experiments you must write experimental setup that with that picture, then 2 observation and 1 conclusion you can write. For this last one you have 5 observations, you can write that, no worries. Okay. I hope you understand, so please make a note of it. Okay. Now let's come to our topics. So we completed this, the experiment of Faraday and Henry. Now let's come to Faraday's law of electromagnetic induction. What it says about. So do you remember in the Faraday experiment when I was explaining, many times I used the word change in magnetic flux, okay, or change in magnetic field. So this is what basically it is telling. Okay, the law will say that EMF is nothing but that induced EMF. Okay, if current is there, definitely some potential difference will be there. That EMF, that is called induced EMF, is equal to what? The rate of change of magnetic flux. So this is what we will see here in Faraday's law of electromagnetic induction. Okay, so now let's come here. Okay, so now give heading, new heading, Faraday's law of electromagnetic induction. So first law and second law, 2 laws are there. Actually NCERT will check only 1 law is given. Like there is no distinction between first, second. Okay, but you can write here between distinction you can give one first law, one is second law. So what is the first law is telling? Now whenever the amount of magnetic flux linked with a circuit changes and EMF is induced in the circuit. That is what we told. Whenever there is a change in magnetic flux, then induced EMF will be there. Due to that one, induced current will be there. And the induced EMF lasts so long as the change of magnetic flux continues. Induced EMF will be there till you are changing the flux. If you are not changing any flux, there will be no induced EMF. Okay, that is what the second line is saying. So remember this law, remember whenever there is a change in magnetic flux, there is an induced EMF in the circuit. Okay, and if circuit is closed, then that current will produce there. That current is called basically induced current if circuit is closed. Okay, now second law what? Now the magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. Okay, so they are telling here quantitatively telling. Quantitatively what telling? Now the EMF, that is what called basically induced EMF. Okay, is called basically what? Induced EMF. That magnitude, EMF means electromotive force. Remember, many times I am using the word EMF. EMF means what? Electromotive force. Electromotive force. It is actually a potential difference. Motive force. Don't tell it is a force. It is a potential difference. So induced EMF is equal to what? Not change in flux. Time rate of change in magnetic flux. This is what they are telling. EMF equal to this one. Okay. So this is phi is nothing but your magnetic flux. So magnitude of induced EMF equal to d phi by dt. And already we know d by dt, magnetic flux I can write as BA cos theta. BA cos theta. So dA by dt, BA cos theta I can write. Like this also I can write. And if suppose magnetic field is changing, area and cos theta is say like constant, then I can use this thing as basically what? Many way I can use this. I can use like this one, dB by dt A cos theta, or I can use B dA by dt cos theta, or BA d cos theta by dt. Like this also I can use. Okay. So this is the basically induced EMF. So if a magnetic field is changing, that time also induced EMF will be there, because magnetic field change also will be change in magnetic flux. Okay. So these things also you can remember little, but you write up to this one you write. So you can keep this one in mind. You can keep this one in mind. Okay. But exactly what laws basically method actually that mathematically what you can write. Now mathematically if you want to write this law, you can write magnetic flux change, that is d phi by dt, that is rate of change of magnetic flux, and this way we can write. Okay. So what is this negative sign again comes here? Now negative sign will understand from Lenz's law. Okay. So negative sign we will say basically what? Now here the induced EMF is producing in such a that it will oppose the cause of that change in flux. Okay. So who is producing that induced EMF? That cause it will oppose. So that's the negative sign. So just remember that. So negative sign is due to Lenz's law, and this exact formula is like this one, but if the magnitude you are writing, you would write this way. Okay, E equal to d phi by dt. But remember, while solving MCQ and all, suppose flux is given something and you want to find induced EMF and you want to do differentiation and all, and there are both positive negative value in the options, then you use this formula. It is more correct, you use that. But if magnitude they asked, here they mentioned magnitude, that's why magnitude as calculating means negative sign I have not given. But you can put negative sign in exact formula. Okay. So this is about your Faraday's law of electromagnetic induction. Okay. So that means what you are understanding here. Now the experiment we saw in this coil. In this coil now there is a generating EMF in this coil C1, EMF is generating, and that EMF value is nothing but it is now d phi by dt. And what is that phi? Now whatever flux changes here occurring, the magnetic field is due to this coil and the area due to this coil C1. Okay, so like that you can understand. So this is your EMF is coming. Okay, induced EMF. Now from here little we will go further. In that coil or in that circuit, what is your induced current? If EMF you are getting this much, what is the induced current? That one also will see. So please note it down, first law, second law with the definition and mathematical form actually. Okay, and the negative sign you understand, negative sign is due to Lenz's law, and that one we will study in a different section. Okay. Now try to understand here induced current. So what is your induced current in the circuit? Induced current. Induced current will be I you give, that is EMF, induced EMF by R, and induced EMF is d phi by dt. I am writing magnitude wise, that's why magnitude I will put into 1 by R. Okay, so this is the normal formula, V equal to IR you know. Similarly, if induced current you want to find, induced EMF by resistance. So remember R is what? R is the resistance of the coil. Resistance of circuit, of coil or circuit, whatever. Okay, so that is the resistance. Now from here also, if you want to find what is your induced charge, okay, if you want to find what is your induced charge, that also you can find induced charge. Okay, so this is Q. Okay, let me write it is induced, that will be better. Q induced, that will be change in flux by resistance. Okay, so why change in flux by resistance? Because you know induced charge if you want to find, I have to do now I dt. Okay, so I dt, and if I dt I will do dt will get a cancel, will get a d phi by R. So that's why I am writing directly it is del phi by R, or you can write also d phi by R. Okay, d phi by R, or it's a final flux minus initial flux divided by R. That also you can write. Okay, so here also one formula remember, that is your induced current. Induced current. Okay, so induced current and induced charge, all formula we got. So in that circuit, if a change in flux is happening, due to change in flux there is induced EMF, there is due to induced current and induced charge. Okay, so induced current will be 1 by resistance and change in flux, that is EMF d phi by dt, rate of change of flux. Okay, so remember here is what basically telling, now time rate means derivative you to consider. Okay, if magnetic flux is given in terms of t, then you have to do differentiation. Okay, t differentiation you have to do and you have to calculate. Okay, suppose given like this one, suppose just for example I am telling, if it is given like this, if phi equal to 2t plus 3, okay, then find EMF, then find magnitude of EMF, okay. So if this type of things are coming, then what you can do here, now differentiation will take. So EMF equal to, or magnitude of EMF equal to d phi by dt. Okay, if magnitude did not ask here, only EMF asked, so minus also you consider there. So it will be nothing but it is your d by dt of 2t plus 3. So 2t plus 3 derivative will take, t derivative is 1 and 3 derivative is 0, because constant derivative is 0 and t derivative will be 1, so answer will be 2. Okay, so like this you can understand. Okay. And in different situations, different things will be given. So flux you can change in different way. I told, if you change the magnetic field, flux will change. If you change the area also, area of the loop, then also flux will change. So different methods there. So if you want to write also, you can write your EMF can be also written as magnitude of EMF is dB by dt into A cos theta. Okay, or you can write B into dA by dt cos theta. This you also can write. Okay, or you can write also BA. Suppose there is a variation in theta, that also you can write. Okay, or normally you can write basically flux final by flux initial by T. So this also you can do. Okay, sometimes we can use this type of formula to use that. Or if there are n number of turns are there, so if n number of turns are there, for that purpose also you can write the EMF. So let me write here, for n number of turns, for n number of turns, we write EMF equal to n d phi b by dt. This also you can write. If a magnitude is finding, then n d phi by dt you can write. So this is your induced EMF. Okay. Okay. So this all formula, important formula, remember for MCQ and for problem solving. Okay. So induced current, induced charge, and some differentiation relation also. Okay. And next, how many types of changes can happen? So EMF changes can happen, or sorry, flux changes can happen if variation of B with respect to T, variation of A with respect to T. Okay, like that you can understand. Okay. I hope you understand. Okay, let's move on to the next thing. So here you check one NCERT example 6.2 is given. So what is given here? A square loop of side 10 centimeter and resistance 0.5 ohm. So here they are telling a loop is square shaped and side area, suppose side take A is 10 centimeter. Okay, placed vertically in the east west plane. Vertically in the east west plane. Okay, so you know the directions. This is east, this is west, this is north, this is south. Okay. So in this direction, in east to west direction, one plane, in this plane, what is there? Now your square area is there, side is 10 centimeter. Now a uniform magnetic field 0.10 Tesla is set up across the plane in the northeast direction. So basically northeast direction is this one. So this is the northeast direction. So in this case some magnetic field came, suppose. In this case some magnetic field came. Okay. Now the magnetic field is decreased to 0. So field became 0 in 0.7 second at a steady rate. Now determine the magnitude and induced EMF, magnitude of induced EMF and current during this time interval. So what they are asking here, they are asking you find what is induced EMF and also you find what is your induced current. These two they are asking. Okay. And what is given here? Now given that okay, area is not given directly, so side is given. So side means you can write this small a, so small a 10 centimeter and area you write directly. If it is square, so area of square is a square, so 10 into 10 to the power minus 2 square, so will come as 10 to the power minus 2 because it is 10 to the power minus 1 square. So 10 to the power minus 1 square is nothing but it is 10 to the power minus 2 meter square. Okay. So area is given and resistance also given. So this is your resistance. This is a resistance given R. Okay. And magnetic field also given. So magnetic field you check. Magnetic field, that is B. How much B is given? 0.1 Tesla. 0.1 Tesla. So it is SI unit. Tesla is SI unit. So no need to convert anything here. Now next is time given. Some time is given there. Time T is given. What it is? T 0.7 second. 0.7 second. Okay. Now EMF you have to find. So to find EMF, you need to find the flux change. So you need to find the flux change and time already 0.7 is given. So if you can find what is your flux change, then easily you can get what is your induced EMF, because change in flux by time, it will give you induced EMF. So I hope you understand the data here what is given. Now to find the EMF, you need a magnetic field. To find the flux, you need a magnetic field area and angle between B and A. See here, area they are saying is going vertical like this one, and one magnetic field is in northeast direction, means you will check angle, the theta will come 45 degree. So between B and A, angle will come how much? Now theta will come 45 degree, as it is given in northeast direction magnetic field. So between area, that means if I can check like this also. If my area is going like this way, so in this north direction I will have what? I will have my area vector, and here angle how much coming? This is 45 degree. Okay, so theta will be 45 degree. So between B and A, angle is 45 degree. So now I can find the final flux and initial flux. Then after I can get the induced EMF. Okay, so now let's find here. Now see here, your final flux is basically 0. Why final flux 0? Because your magnetic field is decreased to 0. So in the final flux expression, when magnetic field will come, it will become 0 only. Now what is the initial magnetic flux? The initial magnetic flux is BA cos 45. Okay, and B is given, how much it is? B is given 0.1, and A is given already, I calculated 10 to the power minus 2, and here it is 1 by root 2. So if initial flux I'll check, so it will coming how much? 10 to the minus 3 root 2. So here, if you change in flux, I'll check now what is my change in flux. Now it will be final minus initial or initial minus final, anything you can check, but you take with the magnitude wise. Okay, so now it will come as basically how much? 10 to the power minus 3 by root 2. That is my 1 by cos 45 is 1 by root 2. So it is coming 10 to the power minus 3 by root 2. So after finding change in flux, now induced EMF you find. So what is induced EMF? Now change in flux by time or change in time. So change in flux is 10 to the power minus 3 by root 2, and into time is given 0.7. Now understand, 1 by root 2 is 0.7. So here what will happen? Cancellation will happen. So here cancellation will happen and we'll get answer as 10 to the power minus 3 volt. Okay, so 10 to the minus 3 volt. 1 by root 2 is 0.7. So answer is 10 to the power minus 3 volt. 10 to the power minus 3 volt is also called as what? Millivolt. So what I am getting answer here? Now my induced EMF equal to 10 to the power minus 3 volt, or I can tell 1 millivolt. 1 millivolt. Okay. So see, systematically I calculated, to find EMF I need change in flux. To find change in flux I need final flux, initial flux, and as magnetic field is became 0 at final situation, that's why my flux also became 0, because flux contains magnetic field and flux is directly proportional to magnetic field. Then after initial flux is what? BA cos 45. I understood what is my theta, 45 degree. Then I calculated my EMF. And after finding EMF, you can easily get what is your current. So your current will be I equal to EMF by R. So EMF by R means 10 to the power minus 3 volt divided by 0.5 ohm. 0.5 ohm. I will check this one, it will come around 2 into 10 to the power minus 3 ampere or 2 milliampere. So which is better, you put that. Or if your option is given anything like this, you use that. So you got your induced current. Okay, induced current is EMF by R. Okay, induced current is EMF by R. So you got EMF by R. That EMF is 10 to the minus 3 divided by 0.5. So 0.5 will go up, it will become 2. Okay, so it is becoming 2 milliampere. I hope you understand. So here to find induced EMF and induced current, you need to check about change in magnetic flux. How to find that? and time will be given. And you always understand when flux you are finding how the situation is given. Okay, where is the plane, the surface they are telling loop is there, where is that loop? What is the angle it is making with the magnetic field? Okay, with the magnetic field how much angle it is making? Because that only matters here. If little mistake is happening here, total answer will be wrong. Okay, so check on that. So practice at home. Next we'll see example 6.3. So here one circular coil is there, radius 10 centimeter. So radius is given here 10 centimeter, and it has 500 turns. So number of turns in the coil is 500. So capital N value is given 500, and resistance of the coil is 2 ohm. So resistance is 2 ohm given. Is placed with its plane perpendicular to the horizontal component of magnetic field. So what they are telling now, here plane is perpendicular to the magnetic field. So magnetic field B suppose, and a horizontal component of magnetic field they are telling, let me take this BH. So this is the plane, circular loop, radius R. It is perpendicular to the magnetic field BH. And here if you see the area vector of this loop, then area vector of this loop is this way. So BH and A both are magnetic field and area both are in the same direction. So this is the initial condition. So after reading this one sentence, I can understand this is the situation is there, one coil is there, number of turns is there, resistance is there, magnetic field is there, and the orientation is like this. This is the initial condition. This is the initial condition you write. Okay. Now next, it is rotated about its vertical diameter through angle 180 degree in 0.25 second. So what happened here? Now this coil is now rotated. How it is rotated? Now about its vertical diameter. So this is the diameter actually here. Okay, through 180 degree in 0.25 second. That means what happened? Now estimate the magnitude of induced EMF and current. So here if it will rotate 180 degree, it will rotate 180 degree about its vertical diameter, then the situation will become like this. Your final condition will become like this. Area vector will come like this way, and magnetic field will be like this. Magnetic field will be like this. Okay. So about this axis, remember vertical axis means this axis, dotted line axis. So about dotted line axis, it is rotated. It is rotated. Now here if you see what is the angle between BH and A. Now this theta 2 or theta final is nothing but it is 180 degree. But here if you see theta 1 is nothing but it is 0 degree, because both are parallel, here both are anti-parallel. So about vertical diameter it is rotated. Okay. Now initial condition, final condition we have. Now we need to find the magnitude of induced EMF. So what we need to do? Now here we need to find what is our change in flux. After change in flux, we can use EMF equal to N d phi by dt. N d phi by dt. So here first you find what is the flux 1 or initial flux. That is basically BA cos theta 1, and here flux phi 2 is basically BA cos theta 2. Cos theta. And this B is nothing but BH. They are telling Earth's magnetic field, that's why I am writing BH. Okay. Now here what is the things? Cos theta, theta 1 0 degree will put, I will get it is BHA. And if theta 2 you will put 180 degree, I will get it is BHA into -1, because cos 180 degree is -1. Okay. So initial flux, final flux I have.
Now I need to find a change in flux. Number of turns is given and time also given 0.25 second. Okay. Now phi 1, phi 2 value I have. Now I can get what is the change in flux. Now change in flux will be number of turns into, you can tell, final flux minus initial flux, but remember here I am taking magnitude. So here also take final minus initial flux, or flux 2 minus flux 1 divided by dt. Okay. Now here you can write this one, n BH A minus BHA minus of BHA divided by dt. Now if you check this one, it will come 2n BHA by dt. Okay, dt basically time interval, whatever time interval taken. Okay. Now that means your induced EMF magnitude, I am finding magnitude, remember, because in this formula 1 minus also you can give if you magnitude you are not writing. Now see, your final flux is minus BHA, initial flux is plus BHA, because theta 1 0 here, theta 2 180 here. So minus BHA it will be minus 2 BHA, but as magnitude I am taking, so I am taking everything in positive. Okay. Now next, magnetic field, horizontal component of magnetic field already given, number of turns already there, so substitute 2 into number of turns 500, horizontal component of magnetic field is 3 into 10 to the power minus 5, and area of the coil, see radius is given and circular coil means area of the circular coil is pi r square. Now r is given 10 centimeter, so easily you can find here. So pi into 10 into 10 to the power minus 2 square, 10 centimeter square will be like this. Now divided by 0.25. Okay. So I am getting here 2n BHA by dt, and if I substitute all the given values, then I will get my EMF is like this. Now let us calculate it. 2 into 500, it will come around 1000. 1000 into 3, it will become 3000. 1 pi will be there. So in terms of pi you can keep, or pi value also you can substitute. .14. Okay. So do the calculation. After calculation, here EMF will come. 3.8 into 10 to the power minus 3 volt. So you check this correctly. So here 1000 is there, and here 0.25 will be 25 by 100. So you can 4 also you can multiply up, that also you can do, and pi is there. So pi value 3.14 you can substitute, and from here you can get 10 into 10 to the minus 2, it will be 10 to the minus 1. So square is there, means it will 10 to the minus 2 will come here. So here 10 to the power minus 2 and 10 to the minus 5, it will become 10 to the power minus 7. Now other values you check, you will get around 3.8 into 10 to the power minus 3 volt. That means 10 to the minus 3 volt means it is a millivolt. So 10 to the power 3.8 into 1 millivolt. So millivolt answer is coming. Okay. Now next thing is find the magnitude of current induced in the coil. EMF we got. Now what is the current induced? Now to find current, I can get here. To find current, simple formula, I equal to EMF by R, or magnitude of EMF by R. So it is coming 3.8 into 10 to the power minus 3 volt divided by R is 2 ohm, and 3.2 by 2, 3.8 by 2, 3.8 by 2 will come as 1.9 into 10 to the power minus 3 volt by ohm is ampere. So it is 1.9 milliampere. So this is your current. This is your current in the circuit. Okay. So although it is little lengthy, but you can get everything. The main situation is here. If you are not understanding this, then you cannot calculate this flux change. So most of the time in electromagnetic induction, you will use this formula, but here to apply this, you should understand what situation is given, how flux is changing, what is the angle between B and A, what is the angle between B and A in final condition, in initial condition, like that you have to check. Okay. I hope you understand. Now next come to some MCQ questions. Okay. So a conducting loop is placed in a uniform magnetic field with its plane perpendicular to the field. An EMF is induced in the loop if it is translated, it is rotated both A and B, and it is rotated about its diameter. First understand the picture what given. A conducting loop is placed in a uniform magnetic field with its plane perpendicular to the field. So this is the magnetic field B and this is the loop plane. Okay. Now here perpendicular thing is there, 90 degrees is there. Now they are telling, if I will translate this loop, this loop will go like this, then what will happen? Induced EMF will induce or not? It will never induce. Because in translation also no changes is there in the flux. Because to induce EMF, you must need change in flux. You must need what? Change in flux. Yes or no? It is rotated about its axis. Now see, this is the ring, this is the axis. This pen is axis, this hand is ring, or this one is the ring suppose. This is the axis. Now if it is rotated about its axis like this, it is rotated, then nothing will happen. Because magnetic field will be always like this direction and it is rotating like this, it is rotating like this. So nothing will happen, no change in flux. Because it will not, in initial condition, final condition, same flux, no change in flux. So it is rotated about its axis, it will be not correct. About axis means this axis. This is the basically axis of the coil. This is the axis of the coil. Then if this both answer is not correct, then definitely D will be answer. It should rotate about its diameter. So that means here, if I will take a diameter like this, okay. Now if it is rotating like this, field is like this one, it is rotating like this. So there will be flux change because sometimes this area vector and magnetic field, they will have different angles between them. Okay, so your D answer is correct. Okay, D answer is correct. Now come to the next question. So remember, while flux change questions they are asking you, understand the concept. Next question is, a conducting circular loop is placed in uniform magnetic field. So circular loop, magnetic field is given with its plane perpendicular to the field. So same condition, circular loop, this is the magnetic field. So plane is perpendicular to the magnetic field. The radius of the loop is made to shrink at a constant rate, 1 millimeter per second. So what they are telling, suppose let's radius is r, this radius is changing with respect to time, it is given 1 millimeter per second, 1 millimeter per second. Okay. Now the induced EMF when the radius is 2 centimeter, how much? Now here also one radius value is given, that is 2 centimeter. Okay, so this is all are given data. So given data is this one. Now they are asking magnetic field also given here. This magnetic field is 0.025 Tesla. Okay. Now you can understand also like this way. Suppose this is the magnetic field here, this is the magnetic field, this is the magnetic field like this. and your loop is like this one, small loop, the big loop, like that one I am telling. Try to understand here. So previously this loop was like this, the bigger one is the previous loop initial condition, and it is shrinking, and it is becoming small loop. That shrinking rate is given. Okay, so that means loop is becoming like that. Magnetic field there, loop is big loop, then loop is small loop, big loop, small loop, like that. If it is happening, definitely there will be flux change. Okay, because when it is big loop, there are more number of lines will come inside that, but when small loop, there are less number of lines. So that's why here flux change is happening, definitely induced EMF will produce. So answer will be non-zero quantity. So all options are non-zero is there. So we'll see now how to calculate this. Now we use our direct formula, EMF equal to N d phi by dt, but number of turns is not given. So magnitude, let me write directly d phi by dt. Now next is, I don't have a phi, direct phi here. So let me write here d by dt. Phi is nothing but it is BA cos theta, and as here plane and B are making 90-degree angle, then area vector will make 0-degree angle with B. So it will be cos 0 will be 1. So d by dt, I will get only BA. Now next is area. So d by dt of B, area is nothing but it is pi r square. Area is nothing but it is pi r square. Pi r square. Because circular loop, already I told, if a circular loop radius is r, then area equal to pi r square. So instead of A, I will write now pi capital R square, because r is radius. Now here my EMF will come, B will come out, pi will come out, it is dr square by dt, dr square by dt. Now EMF equal to B pi. Okay. So my radius is changing with respect to time. So r square I cannot take out of the derivative, because r depends on t. So to do differentiation, if we will do differentiation, we will get here 2r dr by dt. Now let us write here EMF magnitude equal to 2b pi r dr by dt. So this is my EMF. Now everything is given here, dr by dt given, r is given, b is given, 2 pi we know, 2 and pi value is 3.14. So now substitute everything, EMF equal to 2, b value is 0.025 and pi value is 3.14 and r value is given 2 centimeter. So there you have to take care, because here all are given in microvolt and all. So let me complete. This one is 2 into 10 to the power minus 2. 2 centimeter is 2 into 10 to the minus 2 meter. Everything in SI unit I am calculating. And into 1 into 10 to the power minus 3, because 1 millimeter per second I can write as 10 to the power minus 3 meter per second. So now this is my EMF. Now if I will see my EMF, here actually 3.14 value they did not apply here. So let me keep my pi as pi, so that I will get in pi answer. Now multiply here 224 and 0.25 into 4. So it will come 1 by 10. Yes, 224 and it is 25 by 1000. So 100 by 1000 is 1 by 10. So here 1 by 10 means it will become pi into 10 power minus 6 volt. So pi into 10 to the power minus 6 volt means how much it is? It is pi microvolt. Pi microvolt. Okay, because you know 10 to the power minus 6 is called basically micro. Okay, so here 10 to the minus 6 volt is coming, that one I can write as microvolt. Symbol of micro is like this will give. Okay, so pi microvolt. Answer is A. So try to understand the question. Accordingly you proceed. What is given, what we know, and from this how we can relate this. That idea you should have, then you can calculate the answer. I hope you understand. So when a particular question is given about EMF calculation or current calculation, then you check always, okay, what is changing, how flux is changing, what is the initial flux, final flux, or any other method flux is changing, that one you check, then after calculate EMF. Okay. I hope you understand. Thanks for watching. Like and subscribe Vidhyalakshmi NEET Academy YouTube channel. All the very best.